Okay, so today we're going to talk about two things. I guess I put post hocs up first, so we'll talk about post hoc comparisons first. So we got post hocs today and transformations. If you're watching the YouTube video, they're two separate videos. If you're listening here, hello, how are you? It's nice to talk to you. If you're listening on the podcast version, it's one podcast. Okay, so let's talk about post hocs. Let's kill the music there. Okay, what are we doing? Oh, now I'm connected. So, okay, you got a significant F, like we have here in our quiz example. I'm almost certain that that's a significant F. We looked that up, 3 and 16 degrees of freedom. I'm sure 4 is significant. But let's see, 3 degrees of freedom. How many groups do we have here? Exactly, 4. Just yell it out, guys. It's okay. Yeah, 4. It's 4 because you have 3 degrees of freedom, so 4 groups. So we've now found that, and remember our HO is just 2, that all the means are the same, and our HA is at least 2 are different, but we don't know which 2. Now, if those were 3 control groups and 1 experimental group, great, doesn't matter, you don't have to do any post hoc tests of any sort. But so that's our HO, but we don't know which means differ from each other. So as I said, if it's the special case of it's 3 control groups, and it might be for, say, a clinical trial drug study, 3 control groups and an experimental group, then you don't really have to do anything else because you've said, oh look, the experimental group's big, the other ones are small, that's what I thought. Most of us aren't doing that kind of work though, right? Most of us are doing much more boring things. We're not curing cancer. Trying to find out if, levels of processing affects memory and word fragment completion. Doesn't help anybody. It's priming and word fragment completion. That's my most cited paper. So I like to throw that out there. Second author. I just did one of the experiments in the paper. Anyway, still I'm pretty proud of that work. Pretty good work, goddammit. And we had to determine in that case, actually we had a bunch of conditions, and we did have a ton of controls to determine in fact that levels of processing is a tiny but measurable effect. We had to find out which means differ from each other. So it wasn't like something like a drug trial where you probably have, like I said, say 3 control groups and an experimental group. And if that's the case, that pattern of 1 high and a bunch low, that's what you're looking for. It's fine. But usually you probably want to know which means differ from each other. So the first approach you could take is you could just do t-tests, which seems counterproductive, but fine. So you can do a whole bunch of t-tests. Now, if we have our example from the quiz had 4 groups. So with 4 groups, we've got how many t-tests to do? 4 times 3. 4 factorial is 4 times 4. I think we have 12 there, right? 1 to 2, 2 to 3, 3 to 4, 2 to 3, 2 to 4. I think it's actually 6. Yeah, I think it's actually 6. Yes, it's a lot anyway. The alpha is going to go up. Now, maybe you don't want to do every possible comparison. I don't know. But if you're doing a small number of comparisons, like 3 or 4, this actually can work. And what this is it's called the Bonferroni, which sounds like the name of some kind of canned pasta dish from Chef Boyardee. Ooh, what are we having for lunch, Mom? Bonferroni. It just sounds like it, doesn't it? Bonferroni, the San Francisco treat. So, that's an old rice-a-roni ad from like when I was small. Do the Bonferroni tea procedure. What we do is we take 1 over n. N is the number of comparisons we're going to do. So if we're going to do like 3, we do 1 over n times alpha, and n is the number of corrections. So all we're doing here is a t-test, but we're changing our alpha level. That's all this is. Okay, so we're changing our alpha level, and if the problem you might say was, yeah, but Dave, I don't know of any tables that have, let's see, it'll be 0.05 times 3. I don't know, that's not, I can't find that on my table, my t-table. That's why there are special Bonferroni t-tables, okay? So, and of course for us, in any sort of practical sense, we would do this with a computer anyway. On SPSS, for example, you go to the section called post hoc comparisons, and you just click the ones you want it to do. Like, it's really that simple. There's nothing complicated here. So in that case, it's a t-test. So here we go. X bar 1 minus x bar 2, divided, we call it t prime, by the way, divided by 2 over the times the mean square error over n. Right, because mean squared error is an estimate of variance, if you've heard that before. So normally this would be s squared 1 over n1 plus s squared 2 over n2. That's all that is. It's just that we're using mean squared error as our variance estimate. Okay? No one does these by hand. Well, this by hand, yeah, I do that by hand because you don't have the stuff in front of us. But frankly, I could just click, click, click. Yeah, go ahead, do as many as you want. That's what most people do nowadays. They just click all of them. Nothing all that. Questions about that? No one's ever going to make you memorize this formula, like your whole life. Anybody who thinks you should memorize that formula is a pathway. No, seriously, because it's like, it's a t-test. And we're just going to use mean squared error instead. You should be able to just figure that out, first thing. And secondly, everybody just clicks for, nobody ever did these by hand. It's just not something people do typically. Anyway, that's a t-test, it's fine. One approach. We could do something else. We could do something called a studentized range. It's similar. As you can see, instead of using 2 times the mean squared error over, it just uses mean squared error over n, and it says largest minus smallest mean. And then it gives you a value, q. So it gives you this value q, and then what tells you how big a difference you have to find a significant difference, is what basically that does. Okay. But yeah, as you can see, it's very similar to the one from. That's another one. Hey, want to see another one? Of course you do. Screwed up the reveal there because my mouse was in the wrong place. Okay. How about the Newman-Cool's test? This one sounds like it's probably the name of a bar, you know? Where are you going? I'm going over to Newman-Cool's. W. Okay, what this determines is a range again of how big, if let's say this number comes out to be 12, then we look at 2 of our means and say any 2 means that differ by at least 12 are different from each other. So it gives us a number. Just like the last one. It just like says, okay, it's any 2 means that are different by 11 are different. Where do you get this Q? You look it up. It's in a table. I'm not even going to do it. I'm not going to show you examples. No one does these by hand. The point is, what happens is after the anal is done, you get a thing afterwards. It'll say comparisons or post hoc comparisons. You look at them and say, oh look, it says these 2 means are different. Yay! Like it's not. No one does these by hand ever. I have never seen these numbers reported in a paper. People just say, oh yeah, and by a Newman-Cool's test, these 2 means are different. No one ever reports those because they figure, you can figure it out. I gave you the mean squared error. Go do it yourself, pal. Like, that's really, it seems to be the idea. Because I once post hoc tested a paper and I put all this stuff in. And then the editor came back with, no, don't do it. Just say you did them. Oh, okay. So we just get this W number, and it's a range, and it just says these numbers are different from each other. These 2 means are different. Barry, you look concerned. Are you concerned?
I'm still thinking about the quiz and how I messed it up.
Oh, come on. Stop it. Stop that. Okay. The honesty, however, I really appreciate. So any set of comparisons with a range R, that's what I'm saying here is, again, if a number comes up and let's say it's 9, any 2 means that differ by at least 9 are different from each other. Okay? Oh, that's what it's there. There's another one called Tukey's HSD, which works almost exactly the same, but just uses the largest to the smallest. And it's called HSD, meaning honestly significantly different. That's what it means. The HSD test just means honestly significantly different. I'm not kidding, I'm not making that up. That's what Tukey called it. Tukey's the guy that came up with exploratory data analysis. You've probably heard of Tukey. I've used Tukey tests quite a bit. They're a nice mix. Some of these tests are more conservative than others, and some of them are more sort of, I don't want to use the word liberal because it's not really quite the right word, but Yeah, let's go with that. You know what that means. So some of them are so conservative, these tests, that even when you find a significant F in your analysis of variance, it says none of the means are different. And it's like, well, no, they are. And some of them are so, I guess you want to call it liberal, but giving differences is that, oh, I just hurt my shoulder. Rack. I hurt myself lifting weights. Shit. And I keep doing the wrong thing with my shoulder. Just don't move my arm, I'll be fine. Very difficult for me not to move. I think you probably know that. Right. Before I injured myself, really till the end of my life. What was I saying? HSD, different groups, different things. What was I talking about? No, was anybody paying attention at all? No, right? Okay, good. So fine, we'll move on. Oh yes, and some were liberal. That's where I was. So sometimes you'll not find a significant F, but because you're doing SPSS, you just click all the things, do all the comparisons. And it says, oh yeah, there's a bunch of differences. Like, this says there's not any. So you listen to the F first, and then you listen to these. One of the reasons I don't like post hoc tests is because sometimes they contradict the analysis of variance. And I'm interested in the pattern of the data more than I'm interested in individual means. It's good that I have Tyler in my office. Okay. See how quick that was? Oh, yeah, I haven't told you about a whole bunch of other ones. I haven't told you about the Chiffé test that never seems to find differences when they're there, for example. There's the LSD test. Did you not? Least significant difference. They're all very clever statisticians, aren't they? Okay, which one should you use? What most people do is they start their analysis and say, just do all of them. And then I'm going to pick the ones that fit with my hypothesis. Don't do that, please. You're not supposed to go one little cherry picking, things like that. That's not the way you're supposed to do stuff. What you would do typically is, what I would do is I would stick to, first of all, one test within a paper. So like if you're writing a multiple experiment paper, and some of you will someday go to graduate school, you'll become faculty members, research scientists, and you'll be writing papers, and you'll do something and you'll maybe find you need to do post hoc tests. Just don't use different ones in different experiments. Use the same one. What I typically do, I typically use Tukey, but like HSE. But I can also say that I've tried others. Tukey's a nice mix of, it's not super conservative, but it also just doesn't say everything's different from each other. So that's the one I like to use. But your mileage may vary. I would avoid the Chiffé test that you will see in an output from SPSS just because it's so conservative that it says there's no differences when there really are differences. Right? Okay. So that's post hocs. You'll note that I hardly talk at all about them because I think I have a philosophical problem with post hoc tests. Yes, I have philosophical problems with statistics. I'm sure some of you do too. But it's more with the way I teach it. But that's beside the point. I'm kind of kidding, just kind of. But anyway, point is, I think it's important when you do analysis of variance, you're looking at the whole overall pattern. If I'm only interested in, is this group different from this group, just do a t-test and don't do the rest of the experiment. I just don't understand. Of course, I'm a crotchety old man, so I'm different than other people. Questions about post hocs before we move on to talk about transformations? Yeah, it's really... You know what? If I didn't have a data fill, I would tell you to learn this on your own. Seriously, it's... All right, so there's a 14-minute YouTube video.